regulators, finance professors, investment managers, traders, quants, developers, spent a lot of time in Silicon Valley. And what I'm here to do today is kind of distill a lot of the knowledge. This field has grown very rapidly in the last 5 years. I spent a lot of time thinking about what makes neural networks work and why is it that they're not really a black box, and why should we not trust the tools that come to us from Silicon Valley, and actually why is a lot of what we get taught in the business school still very relevant. So a quick question here. We'll do a poll so I can get an idea of where everyone else is on this. What's the difference between machine learning, I'll say AI, put those in the two categories, and statistics? In your view, who thinks that just machine learning is just a black box? Who thinks that it's something to do with the way that we think about the data? And who thinks that it's something to do with essentially just working on big data? Okay, so we're definitely trending towards the answer, which I won't say anything because I might bias the results. So, in fact, as you'll see the results coming in, indeed, if we go back to the slide here, so indeed that is the answer. The fundamental difference between machine learning and statistics is we don't assume that our data was generated by a model. Think about that. Think about tick data. Why should all those ticks, all those message feeds, why should all that news be generated by a model? That's what statistics assumes. So if we go back to the slide here, what we'll see is, in fact, that statistics got it the wrong way around. They started by assuming the data was from a model and then went from there. And that's basically the foundation for all of our Nobel Prize-winning work in the last 50 years, whether it's Black-Scholes model or other types of modeling processes. PCA, for example, assumes that the data was generated by a model. Now, we know with very complex big data, that's very unlikely to be the case. So what are some of the differences? Just very quickly here, and we'll move on to the next question. Statistical inference is really about causal inference, and it's also about how we assume the data. So machine learning does not assume a data generation process, and stats is based on what's called information criteria. It's coming back from the 1950s, from Shaw-Clannon, and stats is really prone to overfitting because it really just didn't think about large data sets when it was sort of designed. Of course, I'm blurring the line, or I'm putting drawing a somewhat polarized view of the field, but it's really important to understand that machine learning is really a generalization of statistics where we relax any assumptions about the data. Okay, so next poll question. What does a neural network classifier output? Is it probabilities belonging to a particular category? Is it just the predicted answer? Is it the answer and the confidence interval? In other words, how confident we are. Which one of these is the correct answer? And this question is not just thrown there just to sort of test you. It actually turns out to be very important for how we think about how machines work. All right, so it looks like we're sort of somewhat indifferent. In fact, in a way, this is almost like a machine predicting different probabilities of different classes. But we're somewhat, I would agree with the first answer here that probabilities are, in fact, the machine is outputting the probabilities of a particular observation to each class. Now, we have to be a little bit careful here. If we go back to the slides. Now, for those of you who don't like math, just listen to me and close your eyes. I've had a student in the business school before tell me, don't do that. And I made him very angry because I put some equations on the board. It upset him quite a bit. Bayes' law is the answer to everything. It's funny, but it turns out that if you start with Bayes' law and say, okay, well, I know what the probability of y, if I know what the probability of x given y is, I know what the probability of my output is, my output being two different states given some input data. X is my input data, y is my output. Suppose my output's just the probability of being a 1 or a 0. Is the stock going to go up? Is the stock going to go down in the next time horizon? Now, it's funny because if you use Bayes' laws now, Bayes' law tells you that the only way that you can get the right answer is if your weights are equal to this term here. In other words, they're equal to these probabilities. In other words, your inputs have to be conditionally independent on the output. So if they are conditionally independent, then you don't need a deep neural network. You're OK using just regression. You're OK using a Bayes, what's called a naive Bayes method. You're OK with one layer of a deep neural network. And it's interesting because a deep network is just at its core nothing more than linear regression. See this term here, this Wx plus b, that's linear regression. You add in some regularization, you've got lasso. You add in L2 regularization, you've got ridge. In other words, deep learning is at the core something we already know and understand. And I'm going to explain to you why deep learning is needed. So before I do that, though, it's very important to recognize in big data, alternative data, you are not going to have conditionally independent variables. As you increase the number of variables, of course you're not. There's going to be a high amount of correlation between your factors, whether they're trading strategies, whether they're technical indicators, whatever you want to put into your inputs. So it's very important to realize that deep learning is really taking off here, or it's had some success, by trying to add layers to decouple the input and try to essentially work around the problem that we don't have conditionally independent data. If we did, we don't need to go any further. So that's the key observation here that we learned just by looking at Bayes' law. And the theory in the breakthroughs in the theory in the last 5 years have really focused on this idea that in fact, your layers are helping you to somehow mix up your input and try and decouple the output from the input a little bit. But if they were perfectly decoupled from the start, we don't need deep neural networks. Okay, next poll. So this will be our final poll. And the poll is, and I'm going to give you the answer to this, why do we need deep neural networks? Now, okay, so it's a very strong perception that it's to do with nonlinearity. I was hoping that would be the case. My next slide. So we move on to the next slide. When we talk about neural networks, we're talking about really only 3 or 4 that really matter in finance. And almost predominantly, we're either talking about memory and time series. That's what that little loop back is on these hidden variables, these blue blobs of things that we don't observe. The reds are outputs, yellow are our inputs. And if there's feedback, then we've got an autoregressive model. It's a time series model. These bottom 3, at least these bottom 2 here, are time series models. The autoregressive model you see in time series analysis is a baby version of these. That's a linear regression right there. That's a logistic regression. Call it a feed-forward network with one hidden layer. It's a logistic regression, plus some regularization, so it's a lasso and logistic regression. An autoencoder is a generalized form of PCA that doesn't assume any Gaussian properties of the data. Why? Because machine learning doesn't make any assumptions about your data. PCA does. So this is the generalization of PCA. And we generally, no one really, I don't know, I'm not sold on the other 2. So let's see what they do. Right, here's my simplest possible network, no hidden layers. Here's 2 inputs with 1 hidden layer and a final output, so it's just going to predict whether it's a 1 or a 0. And then I'm going to do 2 hidden layers. And I'm going to apply this to the half-moon problem. So I'll get to the answer of why we need deep learning. So here's the famous half-moon problem. Can I find a line that separates these orange and these blue dots here? You could map this onto, say, stocks, 0s and 1s. I mean, obviously you don't have that kind of shape in your input space. There's my 1 hidden layer. There's my 2 hidden layers. And for some reason, I mean, neither of them are very good. Now, of course, you could say, well, that's interesting. Why wouldn't it separate as I have more layers? And the answer is, well, that's not the role of the hidden layers exactly. So why do we need... So firstly, why do we need more neurons? Why did that example I just showed in the previous slide not work? I have a hidden layer. Well, it's precisely because we need to project our data up into a higher dimensional space first. And then we look for a line that separates out in that space that you and I will never visualize. And then the machine projects back down, and that's what it looks like. As a result of going through and projecting up into the dimensions equal to the number of neurons in the layer. I just have one layer here. I'm now able to separate out that line in that projected space. And then when I go back into my original space, lo and behold, we found a very nice representation which separates the two. Now, I needed quite a few neurons here. So the number of neurons in each layer provide the nonlinearity. And in fact, if I turn off what's called an activation function, the entire network is a linear regression. No matter how many layers I add, no matter how many neurons I add, it's the activation function which is performing the role of introducing the nonlinearity. So the answer is, why deep learning? Well, one hidden layer is probably enough to provide enough discriminatory power. However, to interpret what the hidden layer is doing, it's good to have a second layer. As I just did there, I introduced the second layer just to see what the output from the first hidden layer did. Now, of course, I'm not saying you don't need deep learning, but I'm saying let's not dismiss the power of just having a lot of neurons in one layer. And the extra hidden layers are because we want to introduce and decouple somehow the input and the output from each of the layers. It turns out to be very important for why these methods work. And so it is a tool for big data because we can separate out these different layers. So the answer is, yes, you need layers to express nonlinearity, but I would argue that if you have enough neurons in your first hidden layer, that's probably enough. The difficulty gets if your inputs are very highly correlated. Then I would say go to more layers. So we're starting to get some ideas about how to use these, but keep in mind that one hidden layer network is really just a lasso, or it's just, at its core, is just a lasso, or it's something else, and we can interpret those weights in one hidden layer. And if we add the extra hidden layer, we can see what those weights are doing. So we have some notion of interpretability. Now, whether you are a statistician and you disagree with me, of course. But I would argue that all the things we've been said so far, told, that they're black boxes, we don't know what goes inside, we shouldn't really care about it, we don't know anything about the science behind it, they've got nothing to do with statistics, or it's somehow loosely related to statistics. I would say all of these things are wrong. I'd say that the most important thing is to understand what is happening geometrically as these networks add more neurons, how they're solving our problem. So this is our recurrent neural network, and it looks like a mess. And there are all sorts of engineering extensions of this, which are just, I think, could be useful, but we have no idea what they're really doing right now. This, by the way, even as a time series method, it assumes your data is stationary. There's nothing dynamic about this model. Even though people are using it, it assumes the data is stationary. And if you throw this into TensorFlow and you download the TensorFlow or you use PyTorch or any of the other Silicon Valley tools that are fantastic from an engineering perspective, there's no guarantee that you'll get weights which ensure that data in the past is less important than more recent data. It will just spit out the weights that optimize some function, which we know from 101 time series is not the way. If you've done Dickey-Fuller tests and that sort of thing in stationarity tests, you'll know that that violates some of the most fundamental assumptions about time series. So let's look at some applications in the remaining time. And I wanted to say nothing more than that we need to be careful when using those tools, and we need to be careful about assumptions about the data. We don't just get to use these tools without understanding what they're doing. Which I'm sorry to say, because I was hoping there would be a magic bullet and we wouldn't need to sort of break down and understand these things. Now, my focus is primarily on execution. I've visualized some limit order book data there. So the y-axis is the time scale. I'm modeling the liquidity imbalance in the book, because I know it's important for execution purposes, book pressure. So when you see it's getting red, it means that there's a lot of skew in the book, and then we'll see the book move. So every time you see this line here moving, it means that the book is moving, so the mid-price is constantly adjusting. And we can ask questions, with all this data, how can we use neural networks to predict, say, price movements? So we could better adjust our positions if we're quoting or executing at the right level of the book. So there's one example there where what we do, if we're going to do this job properly, is we're going to compare deep neural networks with logistic regression. We're going to compare them with Kalman filters, and we're going to see the trade-off between using recurrent versus feed-forward. And I'd only use a recurrent neural network if I'm fairly convinced that there's a lot of history in my data. And we can do statistical tests first to determine what the parameters of my neural network are, what the look-back period is. And then we do the fitting. There are ways which we can just throw everything into a big soup, which I call the big sweep, and we hope that the machine finds the best look-back parameter, the best regularization parameters, but you end up with this almighty high-dimensional optimization problem, which is pretty ugly to solve. So we can build up different feature sets. Starting with liquidity and balance, I can pull out order flow from, say, Quants paper. I can look at spatial temporal data sets, where I look at all of the book and view it as a spatial data set. And we can compare against our best standing, what's called elastic net, which is elastic net's lasso plus ridge. It's lumped together. It's a hybrid method. It's a linear method. We saw lasso earlier in one of our keynote speeches, or earlier talks in the morning. And then we compare, and we're always comparing against white noise. And if our number is below that, then we're in trouble. We've done nothing. And there are tests called Mariano-Diebold tests, and also we can use chi-squared tests to determine whether our results are statistically different from white noise. Very important in terms of whether we've actually got a solid machine learning method. So it's built up systematically. I always go back to comparing logistic regression. Of course, that should be the same as my deep neural network with one hidden layer. OK, and then finally, what I want to say is, we can look at other examples, pretty more pertinent here. So we can start to, say, use all the S&P 500 returns across every single stock, and we can start to, say, predict whether directionally our portfolio returns is some weighted combination here. I've just picked equally weighted. Suppose we construct a portfolio. We want to predict whether directionally the market's going to move up, or the portfolio is going to increase, or go down, or stay the same. And the idea always with neural networks is to maximize the capacity of data it sees. Never provide it an index. Always provide, or on its own, always provide as many data points as you can. And so as usual, what we're always trying to do is compare in-sample with out-of-sample performance to assess overfitting. In other words, if my model did well in-sample, suddenly performs well out-of-sample, it's an indication that I haven't got enough regularization in my model, and I need to tune up or crank up the regularization. It's also an indication that your data set's varying a lot. And there are now tools to say how different your in-sample data was from the out-of-sample in a more sort of information theoretic sound way. So we can compare logistic regression. Typically, in these classification problems, we like F1 scores because they're a very robust way of measuring performance. Accuracy can be very unreliable because your data can be imbalanced. You may observe a lot of periods where you have zeros, ones, and minus ones. And I'll just say very quickly here that, of course, you should always then look at the differences. And what we tend to see is better out-of-sample performance with the deep neural networks. And that's if you've done the job right. And it's all about using the right performance metrics. It's always starting with something simple and then building it up so that you can always explain the differences between what you've done. It's not just a big soup that you just hope sort of magically washes out the answer. So those are my 5 sort of takeaway points. In particular, if you're using open source tools, be very careful with the results if you're dealing with time series. Going forward, we're going to see a lot of things coming out of Silicon Valley. Uber and Lyft are predicting, ETAs. They're predicting demand. There's a big push for very advanced time series methods coming from Silicon Valley. We're going to see these in the finance sector, sequence-to-sequence models. But we need to understand how they work. And so that's really what this talk is about, is going systematically through and seeing how these things map onto what we already know. Thank you.
We have time for maybe 1 or 2 questions. If you have a question, raise your hand. We have one right here.
Hello, and thanks for the very densely packed presentation so far. One question I have is, all the regressions questions, they give us one sort of stable answer, but when we train a neural network, usually we don't really get one global optimum. We get so many different answers with different predictions. What do you feel about that? How do you see that adding value, or how to differentiate between them?
Yeah, I mean, my answer would be, the following. I mean, so of course, if you're going to a big data set, And you have, we introduce nonlinearity, which is what deep learning does over, say, logistic regression or standard regression. Then, of course, you're solving a global optimization problem. And there's, by definition, there's no guarantee of you reaching a global minimum. I would say, therefore, you need to be very consistent about how when you're testing, you need to test under different weight initializations. Right? How you initialize the network will change the result. So you need to build that into your testing. And I think you always need to go back to something that you know has a global optimum. And just check that at least the code, the implementation, reproduces what you know should work. And then sort of move forward incrementally. But of course, that's going to be a problem with any sort of as soon as you add nonlinearity. And it gets, I don't know whether it gets better or worse as you increase the number of dimensions. But of course, you can always turn the method off and see what optimum it finds. And then you could always perturb one of the weights slightly and see whether, where the source of instability is.
We have one question over here.
Hi, good afternoon. Great talk. My name is Michael Beal from Data Capital Management. Around the question that you talked about of in-sample versus out-of-sample and the actual underlying data just being totally different, something that we see in our world that Uber won't. So statistically, you know that that's the case. I'd love for you to expand around some thoughts as to how you think about approaching that once you find yourself in that world. In particular, do you think about adjusting parameters and methods to deal with that, or do you think about reconstructing your in versus out of sample to have a more normally distributed and consistent data set?
Yeah, I mean, I think we're running out of time, but the quick answer is, obviously cross-validation is meant to assess your models out of sample. It's generalizable performance. And there's something called the KL divergence. It's a way of comparing your outer sample with your in sample and saying how different they are. And so, in effect, what all this machine learning is doing is it's essentially trying to give you some indication of how different your input is from your outer sample and your in sample data set. But there's other ways of doing that. As I mentioned, there's a KL divergence which will do that. And I think it's very important to at least have that as a data point in your figure when you're showing outer sample performance of your strategies versus in sample. How much did your underlying data actually change? Because why would the strategy perform as well? So I think that's something that's missing when we report performance of strategies.
Great, Matt. Thank you so much.
This is Raven Pack.